Hello everyone, this is Professor DiPaolo. Going to run through a couple more problems here. This is going to be the single sample z-test in comparison to the single sample t-test. So we know with the single sample z-test, we need to know sigma. So we need to know sigma, the population standard deviation. So, z-test, need to know sigma, which is the population standard deviation. So if you don't have this, you cannot use z. And in the vast majority of time, we do not know sigma. So if you're doing a research, rarely do you know the population standard deviation because the population is so large that it becomes very difficult to measure it. Now, you may know it if you're dealing with census data, which is basically a collection of, demographics for the entire country, state by state. So if you wanted to compare something to the mean of the state level and you had census data, you would know sigma. Right? Because the census is supposed to be about everyone, the entire population. If you had something like IQ, you may know sigma because the IQ test has been done so many times with so many different people that we have a pretty good representation of what the population mean and the standard deviation is. But if you're running a research study that hasn't been done on a mass scale before, you generally don't know sigma. So that's an important thing to keep in mind. If you look at SPSS, you can't even test a single sample z-test. It's not even in the menu, right? I mean, there's single sample t, but there's no option for single sample z-test because most of the time you're not using it. So it's not even as a menu option. So that tells you how rare it is. If you're using a t-test, you do not know the population standard deviation. So do not know sigma. Right? And that's the main difference here. Z, you know sigma. T, you don't know sigma. So what happens is with the t-test is if you don't know sigma, you need to estimate. So you need to estimate using the sample standard deviation S. And when you estimate using S, you lose degrees of freedom. So for every estimate of sigma, so every sigma you're estimating, you're losing 1 degree of freedom. So in the one sample test, you're only estimating 1 sigma, which represents the one population that you're comparing it to, comparing your one sample to. You're comparing one sample to one population. So you're only estimating 1 sigma value, therefore you lose 1 degree of freedom. So the degrees of freedom for the one sample test is n minus 1. If, however, you're doing the independent groups t-test, you're estimating 2 sigmas. You're estimating sigma for group 1, sample 1, and you're estimating sigma for sample 2 because you're comparing those 2 samples. So in that case, you're estimating 2 sigma values, and therefore the degrees of freedom is n minus 2. Right? So you lose a degree of freedom for every sigma you estimate. Think of that as a penalty, basically. You're being penalized because it becomes harder to reject the null hypothesis using t than it is for z. Now, if your sample size is infinity, which it generally is not, but as your sample size approaches infinity, t will become z. So at infinity sample size, there's no difference between the t-test, the t distribution and the z distribution. However, we don't have infinity samples, so t will be less powerful, right? So it's going to be harder to reject the null with the t-test, and obviously it gets easier as the sample size increases. So as the sample size increases, t becomes more powerful, and with large samples it approaches z. So let's walk through the difference between these two problems here. So in this first problem, a researcher believes that the height of adult males has changed over the last 30 years. A sample of 9 males was gathered. The average male height 30 years ago was 70 inches with a standard deviation of 3 inches. So here we have a sample of 9 males and their heights. And we're comparing it to a population with a mean of 70 and a standard deviation of 3. So here you have sigma. So you have the population standard deviation. So once you have that, you know it's Z. And we know the one sample Z-test, Z equals the mean of the sample minus the mean of the population over sigma, the population standard deviation, divided by the square root of n. So in this case, the mean of the sample we have to compute from this sample, so I'm going to do that in R Studio. So I find mean of heights 70.78. So the mean of that sample is 70.78. Mean of the population is 70. The sigma here is 3. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 as my sample size. So this becomes 0.78 over 3 divided by 3, which is 1. So this becomes 0.78 as my final score. So that's my Z-score. Now I have to compare it to a critical value. Well, is it one-tailed or two-tailed? Well, I'm looking at here changed. So changed is a non-directional term. You're not saying increase or decrease, you're saying change, so therefore it's two-tailed. So I want a two-tailed Z-crit at 0.05. So let's do two-tailed, 0.05, because it's non-directional. And these are the ones you have to remember. So with 0.05 two-tailed, it's going to be plus or minus 1.96. So you're always going to have two critical values when you're doing two-tailed test. So here it's plus or minus. If you're doing one-tailed, you're going to have either plus or minus. You're going to have one value. With two-tailed, you have two values. So here is the sample. Here is 0. Here's positive 1.96. Here's negative 1.96. And our value here is right here, 0.78. As you can see, 0.78 is not more extreme than either critical value, so it's not in the tails of this distribution. Not more extreme than the positive 1.96. Of course, not more extreme than negative 1.96. So here we're going to fail to reject the null. And we're going to conclude that the heights of the current sample is not different than the average height of 30 years ago. Now, this is the two-tailed version, so I'm going to write the box down here of the values. So these are the values you need here. So one tail, 0.05, is going to be either plus or minus 1.65. I'm going to draw a line here. One tail, 0.01, is either plus or minus 2.33. Two-tail at 0.05 is going to be plus and minus 1.96. And two-tail at 0.01 is going to be plus and minus 2.58. So those are your critical values for Z. And that's it. Right, whether it's one-tailed or two-tailed, These are approximations, and they're rounded, right? So these are your critical values that you need to memorize. So 1.65 plus or minus 2.33 for 0.01, for 0.05 two-tailed 1.96 plus and minus for two-tailed 0.01 is 2.58. And this is not remotely close to the critical value here. So we fail to reject. So that's the one sample T. So let's look at the next one. The professor wants to know if her introductory statistics class has a good grasp of basic math. 6 students are chosen at random from the class and given math proficiency test. The professor wants the class to be able to score above 70. Does the class score significantly greater than 70 at the 0.01 alpha level? So here we have 6 students' scores, and we're looking at a comparison mean of 70. So we're comparing the sample mean to 70. We do not have the standard deviation here of the population. So since we do not have the standard deviation of the population, we have to use T. So this is going to be one sample T, which is going to be the same as the top here, mean of the sample minus the mean of the population over S divided by square root of n. So S is approximating sigma here. So let's find the mean of these scores here, which I will do in R. So we're going to call that score. So that mean is 79.17 for the mean. The population mean is 70. Why did I pick 70 again? Just chance. There was no, I know there's 70 was up here. That was just, I don't know. 70 was passing and 70 was average height. It's probably going to be the same. And now the standard deviation. We have to compute the standard deviation here. So let's walk through that. That's a little bit more work here. So we know that the mean is a decimal. So if the mean is a decimal, I do not want to use the deviation formula. I want to use the computational formula. So this one's going to be a little bit more work here. So I need an x squared column. So let's take all these scores and let's do score squared. Let me move this out here so I can copy it. And I failed that time. Just so I can have the 3844. That way I'm not copying anything wrong. Oh, that didn't work. Three 8464. Sorry, my Windows update came in here for whatever reason. 5625. It's 8464. 5625. 4624. 6889. And 9025. Now I want the sums of both of these columns. So sum of score first, and then sum of score squared. $38,461. So 475 for the x values, So this sum of x is 475 here, and this sum of x squared is going to be 38,471. So now we got to compute the sum of squares. So let's go down further here. And I'll come back up and finish the problem. So we know this is the formula we have. Sum of the variance formula. Let me write the variance formula instead. So variance is the sum of x squared minus the sum of x quantity squared over n all over n minus 1. So the numerator here is the sum of squares. So I got the sum of x squared here, 38,471. I got 475 as my x. That quantity squared over 6. I think we have 6 data points, right? Let's see. We have 1, 2, 3, 4, 5, 6 data points. Okay. And this is all over 5. N minus 1 is 5. Bring it down, 38,471 minus, let's do 475 squared over 6. That's 3,764.17. 3,764 all over 5. So let's do that on the top. 38,471 minus this value here, 37,604, 866.83. This is over 5. $866.83 divided by 5. 173.37. There might be some rounding depending on how you rounded it. Rounding error. Not an issue. That's our variance. And then we want our standard deviation, so simply take the square root. So S is the square root of 173.37. S is going to be 13.17. 13.17. Now we're just going to check. And that's exactly what R gives me when I check it. Okay, so we're good. So that's our S, 13.17. Let's go back up here. Put in 13.17. Put in our N, which is the square root of 1, 2, 3, 4, 5, 6. So T becomes 79.17 minus 70 is 9.17 divided by 13.17 over square root of 6. 5.38 rounded. So let's do that. 9.17 divided by 5.38. Uh-oh. What's that happen? 9.17 divided by 5.38. 1.70 rounded. To do decimal places. That is our t value. And then I just check it here. Score 70. Sorry, R is blowing up a bit here. It's blowing up again, so I'll come back to it afterwards. So 1.70. So now we have to look up the critical value. So we know the degrees of freedom is n minus 1, so degrees of freedom here is 6 minus 1 equals 5. So I got 5 degrees of freedom. Now I'm looking for significantly greater, so that's a one-tailed test at 0.01 alpha. So I want T crit 0.01 alpha, right, for degrees of freedom 5. So I have to find the table. So here's your formula sheet and table. I want one-tailed because it's directional. We're looking greater. So you're going to use the top row here. We want 0.01 in the top row. And I want 5 degrees of freedom, which is right about here. Right. 3.365 positive. 3.365. So T crit is positive 3.365. Now we know it's positive because we're looking at greater. Greater means positive, right? Lesser would be negative for the critical value. We know it's one-tailed because I'm looking at a directional here because of greater. We know it's 0.01 and we get 3.365 because we find 0.01 one-tailed. We move down to 5. It's 3.365. That's a pretty steep t value, critical value. So let's look at our obtained value compared to our critical value. If you want to draw the little curve, here's 0. Here's way out in this tail is 3.365. It's way out in the tail. And then 1.70 is right here. 1.70 is not more extreme than 3.365. So since 170 is not more extreme, it's also not in the tail here. So therefore I fail to reject the null. And if I fail to reject the null, I say that the class scores are not significantly greater than 70. Which is kind of a disappointment because that means people didn't do as well as you would like them to do. So the class scores are not significantly greater than 70. And you're done. And that is the one sample z-test and the one sample t-test. And hopefully that's very clear. Let me know if you have any questions, email me. If not, I'll see you online soon. Bye for now.